Welcome back to part 2 of lesson 3.1. This is exponential equations, and these are some applications we're going to talk about. These are 4 formulas that, yes, you need to have memorized, and you need to be able to apply them, and we'll do some applications, specific applications in just a second. But I want to pull apart the equations. I think if you understand the parts of the formula, it sometimes helps you in memorizing them, and it helps you apply them. So the first one we're going to talk about is compound interest. Now the compound interest formula gives you the amount of compound interest, but the P, the first unit it uses, is referred to as the principal. And the principal is the initial number that you're going to start with. It's usually an amount of money. All right, the initial amount of money that you're investing, that you're starting. And the R, as you can guess, is the rate. And this rate needs to be written as a decimal. Remember, and it's usually a percent. That means it will need to be moved twice. Let me zoom in a little bit more here. All right, the N is the number of times that it's compounded. So the number of times it's compounded. And it may tell you it's compounded yearly, so that would be once, or monthly, then it would be 12, etc. The T is going to be the number of years. So you need to remember if it says every 6 months, then this would be 0.5. Notice there are 2 n's in the equation, in the formula. You need to remember that there are 2 n's. Now let's talk about it if it says continuously compounded. And that's important, because if it just says compound interest, you're using this formula. But if you see the word continuously, that's good old PERT. And you've used PERT before. Okay? You've used that in your other classes. Now, we had some formulas earlier. We looked at the graph for exponential growth. Exponential growth and decay. Here, your n sub 0, that is going to be your initial amount. And this is more of an amount of a bacteria, for example, or of a population that you start with, the initial amount. Your rate here is still in a decimal. They all are. Okay, you're always using the decimal, even in the PERT. And the time. Now, if you'll notice, this is plus or minus R. Now, that's important because if it's plus or minus R, depending upon the type of R you have. If you have an R that's greater than 0, then you have a growth equation. If you have an R that's less than 0, you have a decay equation. Bacteria that's growing or population that's declining. Okay? Now, if it says you have a continuous growth or decay, then you notice that you have the E. Now, notice the pattern here. If it says continuously compounded interest, you have the E to the RT. Continuous growth or decay, you have an E to the KT. Well, that K is like your rate. All right, that K is also a decimal. And your N sub 0 is still the initial amount. All right, now you, again, I know I said this before, but I'm going to say it again. You need to have these memorized, and you need to be able to apply them. All right, so I'm just going to highlight them for a second right here, just so that they pop off my notes, because I'm going to now do some applications, and I want to be able to see them quickly. Now, when we did, you typed out your notes, I gave them to you in class, we had some examples that I was going to do with you. Here are the examples. So, if you want to, you can cut those up. I'm going to get this ready for the rest of the notes. I pulled 3 examples out of the book. So this is number 4 on page 162. It will be more helpful if we look at specific examples. So if you have $1,000 and you're invested in an online savings account and earns 8% a year, how much will the account be at the end of 10 years if there are no other deposits or withdrawals and the interest is compounded semi-annually? And then I'd also like you to compound it quarterly, and let's compare them. So let's see what we know right away. We know that the rate, the R, is 8%, and as a decimal, that's 0.08. We know that the P, the principal that I've invested, is 1,000. We know that the time is 10 years. So if I plug that in here to my semi-annually equation, semi-annually means that N equals, if it's semi-annually, that's twice a year. Okay, if it's quarterly, then I know that I have an N of 4 times a year, quarterly. Let's plug it into our equation. And this has the A, okay, the amount that's been invested, see, is 1,000. And we have, the formula tells us 1 plus my rate, which is 0.08, divided by N, which is the number of times it's compounded, 2, times 2 times the number of years, which was 10. Now, when you plug that into the calculator, I would encourage you to start from the inside and work out. So here I would do 0.08 divided by 2 plus 1. Get that answer. Raise it to the 20th. Get that answer times 1,000. Okay, I want you to practice that. You should get $2,191.12. Now, if I want to compound it quarterly, the only thing that changes in these two formulas is the N, right? So the only thing that's changing is that number right there is now going to be a 4. So I have 1,000 times 1 plus 0.08 divided by 4, because it's quarterly, 4 times the 10 years. All right, now when you multiply that again, I would do the 0.08 divided by 4 plus 1, raise it to the 40th, and then times 1,000. And you'll see that if you compound it quarterly, $2,208.04. So that's how much is in the account if it's compounded quarterly in 10 years, as opposed to compounded semi-annually. Let's get another example ready. Next one is problem 5 on page 163. If you have $1,000 invested in an online savings account earning 8%, again, compounded continuously, all right, that's your clue. How much will the account be at the end of 10 years if there are no other deposits? Now we're going to use the PERT, right? So we still have all the same information, but now we're going to start with the $1,000, our initial amount, and we have E raised to the rate, which is 0.08, times the number of years, which is 10. And that value, again, you would work on your calculator, and you have 2,225.54. I really encourage you, I'm not going to make a video where you're watching me type in the buttons, but I really encourage you to practice this on the calculator and make sure you can get to the same value. And there are two different places on the calculator, I will show you that, where the E button can be used. So here, there is an E right here above the division sign, and it's in blue. A little hard to see there on the video. So you can do that. You can do second E, and you can raise it to the power if you want to do that. Also over here, above the LN button, which is a natural log button, above that you will see E to the X. Some people prefer to do that because that automatically raises E to the X, and then you just type in the exponent. So you can do it either way. You can either use this E to the X or you can use this E button. It's personal preference. All right, we got one more example. Last example is number 6 on page 164. This one says the population of a town is declining at a rate of 6%. If the current population is 12,426, predict the population in 5 and 10 years using the model, annually and continuously. So let's first pull off some of the information that we know. This is decaying. All right, this is decaying, so the rates are negative. You need to remember that when we're plugging this in. Negative, there we go. And if I have a rate of 6% and my initial population is 12,426 people, I want to find when t equals 5 and 10. Okay? So first, let's do this annually. Okay, annually, I'm going to have n equals my initial value, my 12,426, times, you remember our formula? This is annually, so this would be 1, and this is a decline, minus my rate, which is 0.06, to the time period. Well, the first one, let's do it in 5 years. And let's see what our value is. And then the only thing I would change would be the 10, right? The 10 years. So let's type that in over here. Let's write that in here. That would be still the 12,426, 1 minus 0.06, raised to the 10th power. So you could do some of this math in your head, but then remember to raise it to the power first before you multiply it by the initial value. Now this should come out to be about 9,119 people in 5 years. Went down that much. In 10 years, if you're checking this annually, it's going to go down 6,693 people in 10 years. Now, if we want to compound it, see if the population is decaying at a continuous rate. So continuously. Then we use the last formula, remember? So continuously would mean we have n equals our initial rate of 12,426 times e to the, and it would be, the rate is negative, so negative 0.06 times 5 years. And then we can do it in 10 years if we compound it continuously. 12,426 times e to the negative 0.06 times 10. Again, please practice this, achieving these on the calculator. This would be 9,205 people in 5 years. And this one comes out to be 6,820 people in 10 years. So depending upon how you want to forecast it, that makes quite a bit of difference, depending upon which way you're calculating the population. This is the end of our notes for 3.1. When you come to class, we'll work on the assignment, and the next unit in 3.2, we get to start logarithms. Thank you.